Hello everyone, my name is Yi Liu, and I will be presenting an overview of the paper titled Distinguishing Attacks from Legitimate Authentication Traffic at Scale. This is for the 2019 summer session of CS6263 at Georgia Tech. This paper was originally presented at the Network and Distributed System Security Symposium, or NDSS, in 2019, and the original paper can be found at this link. As an overview, we'll first start with an introduction about the paper and what it covers, and then we'll give some background on the password guessing attacks. Then we'll go through the details of the estimation algorithm, including the algorithm itself and the sensitivity analysis on some toy examples. And then we'll also discuss the advantages as well as limitations. Then we'll finish with some conclusion. So first, let's have a brief introduction of the paper. So the main problem that the authors wanted to address is how to accurately estimate the odds that an observation X indicates that a login request is malicious. To solve this problem, the authors first developed an algorithm to robustly estimate the ratio of the bad traffic to good among login requests. They also showed how to use this estimate to identify the subsets of the request data that contains least or even no attack traffic. Then they used these least attacked subsets to estimate the distribution of values of any feature of interest over the unattacked data. They put the pieces together to calculate the odds that any particular request is malicious given the observations. And finally, they performed a sensitivity analysis that shows that the odds ratio estimate are very robust even if they fail to identify a subset with little attack traffic. A little bit of background on the password guessing attacks. So we know that passwords are most commonly used means of authentication, as passwords are easy to implement and they are user-friendly. However, password-based systems suffer from various kinds of attacks, and password guessing attacks are just one of them. There are two types of password guessing attacks: offline and online guessing attacks. If an attacker gains access to the password file, he can mount an offline attack by repeatedly guessing a password. On the other hand, in the online guessing attacks, the attacker can't guess at the same rate as in offline, but the number of online guessing attacks are increasing nowadays, so they represent a widespread threat. The online guessing attacks are generally divided into the targeted approach and the untargeted approach. In the targeted approach, a large number of guesses are directed against a small number of accounts. And of course, these accounts are of particular interest of the attacker. The untargeted approach, by contrast, are distributed among a large number of accounts. The attacker is not interested in particular accounts, so he is actually spreading guesses among many accounts. As the guessing is distributed across lots of accounts, the untargeted password guessing attacks can be harder to detect. The most common defenses against online guessing are account locking, such as 3 strikes, which locks an account after 3 consecutive unsuccessful attempts; rate limiting, which throttles the rate at which the server will respond to the guesses against an account; IP blocking, which establishes the reputation for an IP address. But all these approaches tend to work well against targeted guessing attacks, but not for untargeted ones. because the untargeted attacks are able to send millions of guesses without ever triggering these targeted defenses. So, how about machine learning? Unfortunately, there are two factors limiting the use of machine learning algorithms to this problem. The first is the absence of labels, and the second is the non-stationarity of the attack traffic. So we don't have an easy way of getting well-labeled training set of data, and we can't assume that the attack traffic is stationary because the attacker can deliberately change in the traffic patterns to confuse our detection mechanisms. Therefore, it is very important to be able to estimate the ratio of bad to good traffic and calculate the likelihood that a particular observation is malicious. A very important problem here is how to find a way to decide whether to allow or deny a particular access. This decision problem is in principle a binary classification. An obvious fact is that the failed login attempts are much more common in attack than legitimate traffic. But how should we use this fact to protect user accounts? If we have a certain observation, how do we decide whether to deny or to allow? A common way of using an observation to decide between two possibilities is with a likelihood ratio test. So a likelihood ratio test says that if the ratio of the probability of the malicious traffic given the observation X over the probability of the non-malicious traffic given X is greater than a certain threshold T, then we decide that the observation is malicious and otherwise not. The threshold T controls the trade-off between false positives and false negatives. Here, the ML stands for malicious traffic, and the ML bar is for the non-malicious traffic. From the likelihood ratio test, we can also see that simply associating some observation with attacker behavior is not enough for our decision. For example, observing that the probability of X given malicious traffic is high is not enough to allow us to conclude that the odds of being malicious are high. Therefore, how to accurately estimate the quantities in the likelihood ratio test is a great challenge. So here comes the purpose of this paper. So the aim is to accurately estimate the odds that an observation X indicates that a request is malicious. The observation X is the authentication request that the server receives, which normally contains at least a timestamp, the IP address, user agent of the requesting client, the username, and password. So the goal is to find a way to solve the likelihood ratio test, which is, given an observation X, the odds that the value of X implies that the request is malicious. Note that the observation distribution of X, the PX, is the sum of the distribution in the benign and malicious traffic. In this paper, the authors made one assumption about the attack traffic. That is, the malicious logins are a small fraction of total logins, meaning the attacker fail rate is very high. In addition, they made two assumptions about the benign traffic. The first assumption is the rate of login failures from benign users is independent of feature categories. And the second assumption is the distribution of the feature in the benign traffic is independent and varies slowly. This means the aggregate behavior of millions of users is very, very stable. So, based on these assumptions, the authors first started to estimate the last term in the likelihood ratio test, which is the ratio of bad traffic to good. So consider a server which handles login requests. Over any collection of requests, it sees a number of successful logins and a number of failed attempts. The total number of logins, L, are the combined number of benign logins and malicious logins. And the total number of failures, F, are the mixture of benign and malicious fails. So we only observe F and L, but not L sub B, L sub M, F sub B, or F sub M. Now the ratio of fails to logins adjusts F over L, which equals the sum of F sub B over L sub B and F sub M over L sub B over 1 plus L sub M over L sub B. Under the previous mentioned assumptions, the malicious logins are just a very small portion of the benign ones. So L sub M over L sub B equals 0. Another assumption says that the ratio of benign fails to benign logins is fairly constant over a large enough data set. So F sub B over L sub B is a constant. Let's call this constant C. Now the ratio of fails to logins equals C plus F sub M over L sub B. Now, if we divide the data into K subsets, the ratio of observed failures to observed logins in Kth subset can be written like this. And this is interesting because it tells us that the variation of the observed failures to observed logins across subsets or over time are due to the malicious traffic. Then, if we knew the value of the constant C, we then have a straightforward way to estimate the malicious traffic in a particular subset. The ratio of fails to logins for subset K equals Fk minus Lk times C over the product of Lk and 1 plus C. Note that this only involves the quantities that we can observe, the Fk and the Lk, plus the benign failure rate, P, which is the rate at which user enter either password or username incorrectly. Now, apparently we need an estimation of the constant C. Since the malicious traffic can only increase the failure to logins ratio above C, we can get an upper bound estimate for C. Here the minimization is taken over all subsets. Now from this, we can get the estimated P cap as well. Let's call the index of the subset that achieves a minimum failure to login ratio K0. Then we get the estimation of the distribution of X over the benign traffic. Now let's solve the first term of the likelihood ratio test. Recall that any subset of requests has proportions of benign and attack traffic, so the bad portion of the traffic can be written as the total observed traffic minus the benign traffic. and the benign traffic in this particular subset is weighted by alpha k. And the previous part allows us to calculate alpha k for any subset. Now, the overall odds can be written like this. Here, the alpha cap and p cap are the estimated values. So, putting everything together, we have solved both terms in the likelihood ratio test. Now, the likelihood that an observation X indicates that a request is malicious can be calculated. One application of this method might be to deny those requests for which the likelihood exceeds a certain threshold. So for summary, the entire estimation procedure is shown here. We select a time interval and break the request data into k subsets. The first step is to estimate the constant C, which is the ratio of the benign fails to benign logins. Then calculate p cap, which is the estimated value of the benign failure rate. Next, estimate the distribution of X over the benign traffic. Then, for each subset K, estimate the second term in the likelihood ratio test, which is the ratio of bad traffic to good. Then solve alpha K, and estimate the first term in the likelihood ratio test for each value of X. And finally, calculate the post-observation odds as a product of the two. The author then performed some sensitivity analysis on some toy examples. In this example, they supposed the actual benign failure rate, P, is 7%, and they overestimated by about 5%. So here the P is estimated fairly accurately. The figures here compare the estimated value to the actual value. In both figures, the solid lines are the actual value and the dashed lines are the estimates. So the figure A shows the second term in the likelihood test, which is the bad to good traffic ratio. And we can see the estimation is very accurate for all attack volumes. In another example, the actual benign failure rate is still 7%. But the authors fail to identify a subset free of attack traffic, and hence they overestimate P by 20%. Under this overestimation, the method is still very accurate, except for those very small attack volumes. This means that in subsets that contain 10% or so attack traffic, the estimate of the bad to good traffic ratio is extremely accurate, even though they made a grossly inaccurate estimate of P. This sensitivity analysis shows that their estimates are very robust to likely sources of bias. So let's discuss the advantages of this approach. For this method, it had the advantage over the fixed threshold schemes, such as the 3-strike type lockout. Because in those methods, they usually ignore the ratio of bad traffic to good traffic. However, this ratio might vary by orders of magnitude. But here in this approach, this base rate neglect is avoided. Also, it has the advantage over machine learning schemes, and this is because it requires no labels and does not assume the stationarity of attack traffic. While the fundamental assumption of most supervised learning approaches is that the distribution from which the learning data are drawn are representative of what will be seen in the wild in stationery. Well, this approach that the authors presented in this paper has no such assumption. Apart from the advantages, there are some limitations that are worth noting. The first one is this approach requires large scale. And this is because the more accurate the estimation of C, the better the final estimate of the odds ratio will be. And the large site has several advantages in getting an accurate estimation of C. The second limitation is that this approach requires that each category of the feature X be densely populated. This again favors the services with large user bases. Third, if the distribution of X in benign and malicious traffic are similar, the odds may not be useful. It is important to use features that distinguish well between attack and benign traffic. An accurate estimation of the odds is helpful only if those odds are high enough or low enough to allow us to discriminate. And this is, of course, a limitation of all statistical approaches. Lastly, this approach almost always underestimates rather than overestimates the odds of a request being malicious. Thus, the estimates of malice are always conservative and biased towards benign rather than malicious interpretation of the observations. So, finally, the authors concluded that they gave a very simple, robust procedure to estimate the quantities in the likelihood ratio test, including their estimation of the ratio of bad to good traffic. This simple way of calculating the likelihood that any particular observation is indicative of malice can be used to decide whether or not to deny a particular login request. Okay, thank you for watching. And if you have any questions, please just reply to my Piazza post.